Good day to one and all. In this session on nuclear and radiochemistry, we are going to cover some of the most fundamental aspects of the topic. You are already familiar with these terms in your lower classes, particularly your high school and class 11 and class 12, but nevertheless, we will repeat them and reinforce them in the slides to come. But before we do that, it is very important for us to appreciate the enormous and wide applications of nuclear and radiochemistry. I have put together a collection of a few photographs. You can see here a huge nuclear thermal power plant. We have one at Raichur and Kaiga in Karnataka. Now these nuclear thermal power plants are used for converting the enormous amount of nuclear energy that is released into useful electrical energy. But the same extraordinary amount of energy that is released is also used for making nuclear bombs. When the energy is released in a very short time, in the time span of milliseconds or microseconds or even nanoseconds, the energy will cause sudden explosion. So this is the principle on which both the atomic bomb and the hydrogen bomb is based. When you go out and look at the sun, please appreciate that the great amount of heat and light that is generated by the sun and all other stars are due to a reaction called nuclear fusion, in which lighter nuclei come together to form bigger nuclei with the release of energy. In nuclear power plants, big nuclei broke up into smaller nuclei producing energy, but the sun and other stars use the reverse process called nuclear fusion. When you go to a hospital, you are very familiar with some of the different scans that the doctors prescribe to you, like the MRI scan, CT scan, and the PET scan. The PET scan is an acronym for positron emission tomography. Here, positron, which is the antimatter of electron, having the same mass as the electron, but a positive charge instead of negative charge, is used for screening the patient. Now it can provide excellent information about soft tissues which the X-rays fail to do. At the center of the slide, we have a patient who is receiving radiotherapy for cancer. You know that the radiations emitted during radioactivity are definitely very much harmful to human tissues, but they are also very powerful in destroying unwanted tissues, and this principle is made use of in killing the cancer cells. Billions and billions of dollars of money has been invested worldwide in trying to know the nature of the nucleus. We have been told since high school that a nucleus is made up of protons and neutrons, but that story is a story of 70 or 80 years old. Since almost 80 to 90 years, scientists in top research and research facilities and universities across the world, particularly in the US, Europe, and Russia, have been exploring the nature of the nucleus and the various nuclear particles that make up the nucleus. This is the Fermi Lab, one of the best facilities, or perhaps the best facility that the world has in exploring anything minute and small at the nuclear level. This is a snapshot of the kind of particle accelerators that are used inside the Fermi Lab. This is an aerial picture of the particle accelerators that are embedded inside the Earth. To your extreme right is the snapshot of a very famous organization called CERN, which stands for Council for European and Nuclear Research, based in Geneva in Europe. Now this is one of the best facilities where top scientists from across Europe and other countries including India put their heads together to find out what the nucleus is made up of. Recently, in the last 10-15 years, you would have heard about the quest for a particle called as the God particle. That discovery was also made in this particular facility at CERN. So, studying the nature of the nucleus has grabbed the attention of top scientists across the world. In the process, not only have scientists discovered what the nucleus is made up of and are still in the process of proposing various theories to explain the attraction that the nucleus has. But in the process, they have also been able to synthesize various elements which do not occur in nature. Now these elements are called man-made elements. They are also called as trans-uranium elements because they all occur after uranium in the periodic table. And some of the most important man-made elements were made at the Fermi lab in the picture that I have shown. So this gives us a kind of background to appreciate why we are studying radioactivity, applications of radioactivity, and nuclear reactions and the applications of nuclear reactions, both nuclear fission and nuclear fusion. So this brings us to the moot question, what is radioactivity? In a minute I will tell you the fascinating story of how radioactivity was actually discovered. But for the present, let us understand the meaning of the term radioactivity. When the nucleus becomes extremely heavy, it becomes very unstable. So it wants to become stable and achieve a sense of stability by getting rid of some nuclear particles. So a very heavy nucleus will disintegrate or break up by emitting certain particles and form another stable nucleus. Now this phenomenon is what is called radioactivity. The word radio is used here because the nucleus will emit radiation or some kind of a particle which has got very high velocity. So therefore people call it as radioactivity, and that is how we come to know whether a sample is disintegrating or not, only by measuring the radiation coming out of it. This was discovered, of course, by Henry Becquerel in 1896 from the nucleus of uranium, and this phenomenon was confirmed a couple of years later by Pierre Curie and Marie Curie when they discovered two elements, polonium and radium. It should be noted that radioactivity is not confined only to heavy nuclei but also to light nuclei. So some heavy nuclei of course show radioactivity, but even some light nuclei which do not occur in nature are seen to show radioactivity during nuclear reactions. Now, during radioactivity, three types of particles are emitted. Of course, there are other also three main types of particles emitted: alpha particles, beta particles, and gamma radiations. You also have the emission of positron, you also have the emission of neutrons, etc. during radioactivity. I told you that the discovery of radioactivity is very interesting, and it is credited to Henry Becquerel, who found out the radioactive phenomenon rather accidentally. Now this Henry Becquerel was a man who was very much interested in uranium and the compounds of uranium. He was a specialist in studying fluorescence and phosphorescence. So he was doing that with a sample of uranium. Just a few months before, in 1896, X-rays were discovered by Roentgen. So these X-rays were mysterious rays which had the capacity to penetrate through paper and also the tissues of human body. So therefore it had created a huge buzz in Europe and the rest of the scientific community. So Becquerel was obsessed with finding out whether his sample of uranium could produce X-rays. So what he used to do in the early months of 1896 was to take the photographic plate, wrap it with a black paper, and on that put a few crystals of uranium oxide and expose it to sunlight. And then he used to come out after a few hours of exposure, and he used to see a nice impression of the crystals on the photographic plate. So he thought that uranium was actually emitting X-rays. He did this experiment for a few more days, but unfortunately the Paris sun did not give him company. So one day when it was very cloudy, he took the same plate and wrapped it up with a black paper and put the salt and put it in his cupboard in his laboratory, in his wooden cupboard. Then he came back, and when he actually came back, he discovered to his surprise that even in dark without the presence of sunlight, the photograph had clear images of the crystal. He did this with other objects like a metal coin and a nail and other things. So he found out that this uranium salt was capable of forming impression of whatever object that you keep on the photographic plate. So therefore he surmised that this uranium salt should be emitting some kind of a radiation. So he started studying the nature of the radiation. To his surprise, this radiation was affected by electric and magnetic field, unlike X-rays which are not affected. So therefore he came to the conclusion that uranium must be producing some kind of rays. This information was picked up by Marie and Pierre Curie, who of course also lived in Paris, and they started exploring the nature of the radiation emitted by uranium. In the process, they discovered other elements, most notably polonium, thorium and radium, which are all radioactive. It was Marie Curie who first coined the term radioactivity. Now this thread was picked up by Ernst Rutherford and Soddy, who were able to explain the phenomenon based on the fact that heavy nuclei disintegrate and give up radiation in the process, forming stable lighter nuclide. So now we have a broad idea about what is radioactivity and how it was discovered. You must remember that some of the most extraordinary discoveries in science were made rather accidentally. But whenever discoveries are made accidentally, the credit is given more often to chance than to the prudence of the scientist. You must also appreciate this fact that only a prepared mind is able to note the discovery and its importance, and that is the case with Henry Becquerel. There are two types of radioactivity. One that occurs on its own, called natural radioactivity, where the nucleus spontaneously undergoes disintegration. Here I have shown a nucleus of plutonium undergoing spontaneous disintegration, emitting an alpha particle and becoming uranium-236. The other type of radioactivity is induced. It can be made by the intervention of human being. So what we do here is we take a nucleus and bombard it with a high energy particle like an alpha particle or a neutron or a positron or an electron, which of course we'll study later. So in the process, this stable nucleus will capture the projectile or the fast moving particle and form an unstable isotope, which itself starts emitting radiations. Now we'll turn our attention as to the nature of the various particles that are emitted during radioactivity. The first particle of interest is what is called as the alpha particle. Now this alpha particle is emitted from the nucleus of the sample that is undergoing disintegration. It contains 2 protons and 2 neutrons. In other words, it can be treated as the nucleus of helium. Remember, a helium atom is different from an alpha particle. A helium atom has got 2 protons and 2 neutrons inside the nucleus, but it has got 2 electrons outside. But an alpha particle does not have 2 electrons outside. It has simply 2 protons, 2 neutrons, lot of kinetic energy, okay, and therefore it can move with extremely high velocities of the order of 16,000 kilometers per second. Since it carries 2 protons, it is doubly positive. So when you pass it through a gas, it is able to pick up electrons from the gas and cause its ionization. Similarly, when it strikes a photographic plate, it can cause luminescence, which was what was discovered by Henry Becquerel. The second type of particle that was discovered during radioactivity was the beta particles. Beta particles are nothing but electrons, but remember, they are not the electrons found outside the nucleus, but rather electrons emitted from inside the nucleus. Now, of course, you will be wondering how electrons are emitted from inside the nucleus. So during radioactivity or the disintegration of the heavy nucleus, a neutron breaks up, forming a proton and an electron. this electron that is formed inside the nucleus is pushed out and comes out and has been called as the beta particle to distinguish it from the electron found outside the nucleus. So therefore, we will call a beta particle as negatively charged, but we can consider that its mass is 0. It can travel with very high velocities, almost 40 to 60% of the speed of light. Being light particles, they can of course cause ionization much the same way as alpha particles, but since they are very light, they move through the gas and therefore they are not able to cause ionization to the same extent as alpha particles, and hence they have very little effect on the photographic plate. They are generally shown by the symbol beta or beta minus and represented as E-10. You must note that positron is the exact antithesis or the antimatter of electron. It is represented by beta plus or E+10. The third type of radiation, which is often produced along with an alpha or a beta particle, is what is called as gamma rays. The gamma rays are nothing but electromagnetic radiations which carry enormous amount of energy. They are very much similar to X-rays. Their wavelengths are very small. Now you know very well that wavelength and energy are inversely related. Smaller the wavelength, greater the energy. So gamma rays are extremely high energy radiations. Because they are electromagnetic waves, they have neither charge nor mass. So they are not deflected by electric and magnetic field. They have got extremely high penetrating power, even greater than X-rays. They cause ionization of gases, not directly but rather by giving kinetic energy to the molecules of the gas. The figure at the bottom is very interesting, where we compare the penetrating powers of alpha, beta and gamma radiations. Now alpha particles are quite heavy, so they don't penetrate paper, or at the most they can penetrate a few millimeters. Beta particles are quite light and they travel with high velocities, so they can easily penetrate through paper and probably the first layer of the skin, but they cannot enter inside the organs. However, gamma radiations are extremely harmful to human beings because they can not only penetrate through protective clothing and even the skin, but rather pass through the human body. So therefore, and even lead. So therefore, whenever there is gamma radiation in the vicinity, extra precaution has to be taken. This is a periodic table showing you some of the radioactive elements which occur naturally and also some of the man-made or artificial radioactive elements. The most important elements that we have to note in the course of our study in the coming sessions is lead and bismuth. Now lead and bismuth represent a kind of barrier after which the nucleus becomes continuously unstable. So lead is perhaps the most stable naturally occurring nucleus. After that, bismuth shows natural radioactivity. From bismuth to uranium, all the elements that occur are radioactive. They are found in nature, but they survive for a very short time. So three important elements, bismuth, thorium and uranium, show radioactivity for considerably long time, and therefore their radiations can be observed. All the elements that occur after uranium have been synthesized by the effort of human beings and scientists. So therefore, these elements are called transuranium elements. Please appreciate that in the course of our discussion, we will be repeatedly referring to some of the important elements that we use in nuclear reactions, particularly the heavy ones: uranium with atomic number 92, thorium with atomic number 90, plutonium with atomic number 94, bismuth and lead with atomic numbers 83 and 82. So it is advised that you keep a periodic table with you whenever you read in nuclear reactions and try to become familiar with the symbol as well as the name of these elements. because most of these elements are not very much widespread in nature and therefore they are not part of our regular chemical reactions. This brings us to an excellently important definition called isotopes. Now, what are isotopes? Before we define them, we need to define two other important terms. The first being atomic number, the second being mass number. Students often lack clarity about these two terms, so I request your patient attention. Atomic number simply refers to the number of protons present inside the nucleus of an element. Mass number represents the total number of protons and neutrons present in the nucleus of an element. Remember, mass number is a number. It is not the mass of the nucleus, but simply refers to the number of protons and the number of neutrons put together present in the nucleus of an element. So therefore Z is equal to P and atomic mass number A is equal to P plus N, which means that the number of neutrons can be given by A minus Z. Then what are isotopes? Now isotopes are atoms which have the same atomic number but different mass number. In other words, they have the same number of protons and different number of neutrons. Now what is the implication of this? We will take three examples: C12.6, C13.6 and C14.6. Remember, in each one of them, a little bit of mathematics will tell you that there are 6 protons, but carbon 12 has 6 neutrons, carbon 13 has 7 neutrons and carbon 14 has 8 neutrons. So during the formation of carbon at the initial stages of the formation of the universe, various combinations of protons and neutrons were obviously formed. Some were more stable, some were less stable, some have survived to this day and some have not survived. So carbon 12.6 has got great abundance. Compared to carbon 12.6, carbon 13.6 and carbon 14.6 have very little abundance as of today. The only difference between carbon 12, 13 and 14 is that they have different number of neutrons. In other words, they have a different mass number but they have the same atomic number. Since they have the same atomic number and therefore the same number of protons, they also have the same number of electrons outside the nucleus. Carbon 12, carbon 13 and carbon 14 have the same number of electrons outside the nucleus and therefore they show identical chemical property. So you cannot distinguish them on the basis of chemical reactions. Another pair of isotopes shown are uranium-238 and uranium-235, which are of great importance in nuclear fission. Again, you will see that each one of them have 92 protons but different number of neutrons. We will again summarize very quickly the properties of isotopes. As I have already mentioned, they have the same number of protons and therefore also the same number of electrons outside the nucleus. They are chemically indistinguishable. They represent the same element in the periodic table. In fact, that is why they were called isotopes, because they occupy the same place in the periodic table. You can distinguish them using the periodic table. Third, in most cases, isotopes of the same element do not occur to the same extent in nature. In other words, they have different natural abundances in most cases. For example, carbon 12.6 is extremely abundant, the remaining are not. Now some of the isotopes may be radioactive, but some other isotopes may not be radioactive and stable. Carbon 14 is radioactive, while carbon 12 and 13 are not radioactive. The other type of nuclei that one comes across are called isobars. Now this posed some kind of a headache to scientists in the 19th century because scientists those days had developed techniques of identifying elements based on mass rather than on chemical properties. So they found that argon, potassium and calcium had the same mass number, or in other words, they have the same kind of mass. So although they had the same kind of mass, they exhibited different chemical properties. Now they exhibited different chemical properties because they had different atomic numbers. Because they had different atomic numbers, they had a different number of electrons outside the nucleus. You know that the chemical property of an element depends on the number and arrangement of electrons. Once the number of electrons are same, the arrangement is generally the same. Therefore, they have identical chemical, they do not have identical chemical properties. But accidentally, their mass numbers turn out to be the same. Therefore, they were called as isobars, those which have the same mass. Unlike isotopes, isobars do not occupy the same place in the periodic table because they represent different elements, and therefore argon, potassium and calcium have different places in the periodic table. This table will illustrate to you that the number of protons and the number of neutrons need not be the same. 1822, 1921 and 2020 merely underlines the fact that in isobars the number of protons and number of neutrons are not necessarily the same. This brings us to the very first session on nuclear and radiochemistry. I hope you have learned some of the most fundamental aspects of nuclear and radiochemistry, namely what is radioactivity, what are the radiations produced during radioactivity, the nature of these particles like alpha particles, beta particles and gamma radiations, what are isotopes, what is the natural abundance of isotopes, what is the chemical nature of isotopes, and what are isobars. We also have in the process seen what are naturally occurring radioactive elements and man-made radioactive elements in the periodic table. We will be using all these concepts in the coming sessions on nuclear and radiochemistry. I thank you very much for your patient listening and attention. Thank you.